Welcome back to Calculus 3. Today we finish off the present module. We're going to begin with an application of the maximization and minimization process that we've been considering. Suppose that we have a bunch of data points, perhaps seemingly randomly spaced, but having more or less a linear nature to them. Suppose there's a line of best fit that goes through these points. What do we even mean by best fit? First of all, let's describe the data. The data consists of points x1, y1, x2, y2, and so on. We call this bivariate data. The data comes in pairs. Let me give you an example. Suppose I have a collection of data where I have shoe sizes versus, say, arm length. They won't be perfectly linear, but you might suspect that the bigger the person, the bigger the arm length, and the bigger the shoe size. Those might grow bigger together, though that's not always the case, as you must well know. We have bivariate data. We want to try to predict what values will be from one variable in terms of the other. So we would like to fit a line to this data. We'd like that line to fit as best as we possibly can make it fit. Whatever that line is, it will have the form mx plus b. So there are two unknowns. There's the y-intercept b and the slope m. We have no idea what these are. We need to find m and b so that the line matches the data with the least possible error. So let's try to figure out a notion of error that we can use that will lead simply to the line of best fit. We're going to find something called the least squares line of best fit. This may not be the only way to fit a line to bivariate data, but it works and it's in common usage. The idea is, for each of these points, we have the coordinates of that point given as data, but we can also calculate the corresponding line on the line of best fit by plugging in the x value and getting a corresponding y1 hat. This is the predicted y value on the line of best fit. It won't equal the original point, but it will have the same x coordinate. The error, then, is the gap in the y coordinates. What we'll do is we'll find the total error. And to find the total error, we'll take the sum as k goes from 1 to n. It'll be yk hat minus yk. That's the difference between the expected y value and the actual y value squared. So these are the errors in the approximation by the line from the actual data. And we're going to square those, making all of them positive, and add them up, getting the sum of the squares of the error. This is, in fact, the sum as k goes from 1 to n. Each of these is m times xk plus b minus yk. And so the total sum of the squares of the errors is a function of two unknowns, the slope m and the y-intercept b. E is a function of m and b. We would like to find the critical point m and b where the sum of the squares of the errors is at a minimum. There is no maximum. You can make this as big as possible. This will have squares after all, so it's going to end up looking something like this. There's no top, but there should be a singular critical point that gives you the absolute minimum. To find this critical point, we need to take the partial derivatives of e and set them equal to 0. So we'll take dE dB, which is the sum. As k goes from 1 to n, the 2 can come down. We'll leave the inside alone. Subtract 1 from the exponent, and then multiply by the derivative of the inside with respect to b. And that's just 1. Note that the 2 can be factored out of the sum and then divided off. We also take the derivative of e with respect to m and set it equal to 0. We subtract 1 from the exponent, and then we multiply by the derivative of the inside with respect to m. That gives us xk. We now have two equations in two unknowns, m and b. The art is learning how to solve equations like this for m and b, but that's not hard. This is a linear system of equations. You've been solving these since Algebra 1. For equation 1, we can rewrite it as, we can break the sum up into different parts. If we add up m times xk's, the m's are all constants that can be factored out of the sum since they don't depend upon k. We'll have the sum of the xk's. When we add b to itself n times, we get b times n. And then we get minus the sum of the y's. On the other equation, we can still factor the 2 out and then cancel it off. But we must also distribute the xk's to each term. We get m times the sum as k goes from 1 to n of xk squared, plus b times the sum as k goes from 1 to n of xk, minus the sum as k goes from 1 to n of xk yk. This is our two equations and two unknowns, m and b. We're going to write this a little differently. There are some standard notations in statistics that we are going to apply here. In particular, Sx will be the sum of the x's. Sy will be the sum of the y's. Sx squared will be the sum of the x squareds. And Sxy is the sum of the x times y's. Writing the equations with this notation gives us a lot of simplification. We're going to move these terms to the other side, though. The first equation becomes m times the sum of the x's plus b times n, and we've moved this term to the other side, giving us the sum of the y's. The second equation becomes m times the sum of the x squareds plus b times the sum of the x's equals, moving this to the other side, the sum of the x times y's. We can solve this system of equations by any number of ways. I suggest that we use Cramer's rule. Now, I'm presuming that a good number of you don't remember Cramer's rule, so I'm going to bring this back to your memory. Suppose we have the equations ax plus by equals e, cx plus dy equals f. Cramer's rule says that the solution is x equals a fraction where the denominator is the determinant of the coefficient matrix, whereas the numerator is the determinant of the same matrix but with the x coefficients replaced by the right-hand sides. And the y-coordinate of the solution has the same denominator, but the coefficients are replaced by the right-hand sides. As a quick example, suppose I have the system of equations 4x minus 2y equals 7, and then how about 4x plus 3y equals 5. What is the solution to this system of equations? Well, according to Cramer's rule, I know it would be easy to solve this one by elimination. According to Cramer's rule, replace the x coefficients by the right-hand sides. 7, 5, negative 2, 3. The denominator is going to be 4, negative 2, 4, 3 inside of a determinant. This is going to be 21 minus negative 10 is 31, divided by 12 minus negative 8 is 20. The y-coordinate is found in the same way. The denominator is still going to be 20. The only thing that changes is that we replace y coefficients by the right-hand sides. So we get 20 minus 28 is negative 8 over 20, which we then reduce. Now I know you could have solved this by any number of other ways. We could easily have subtracted the two equations. Multiply the top equation through by negative 1 and add the bottom equation. You'll end up with 5y equals negative 2, which means y is negative 2/5. 4 goes into 8 2 times, 4 goes into 20 5 times, negative 2/5. Same thing. So, how do we solve this system of equations using Cramer's rule? By the way, Cramer's rule is maybe the best way of solving a system of two equations, linear equations, and two unknowns. But if you get much bigger, it is possibly the worst way, involving a lot more computation. If the matrix gets really, really big, the number of computations becomes prohibitive. In this case, m is going to be, let's see, in the denominator we'll have the determinant of the coefficient matrix. In the numerator, we replace m coefficients by right-hand sides. And so we get sx times sy minus n times sxy. Sx is the sum of the x's, sy is the sum of the y's. That's not the same thing as the sum of the x times y's. In the denominator, we have sx quantity squared minus n times sx squared. And again, if you add the x's and then square, that's different from squaring and then adding them. So this gives us the slope of the least squares line of best fit. How about the intercept? The intercept b has the same denominator as before. What changes, of course, is we replace the b coefficients by the right-hand sides. So we get sx times sxy minus sy times sx squared. I wanted to show you how to calculate the least squares line of best fit on a spreadsheet. You have to calculate x squareds and x times y's, you'll recall. I'm going to have some number n. I'm going to enter some data points. I'm going to enter them kind of randomly. 2, 3, 2, 5, 4, 7. That's 6 x's, and now the corresponding y's. How about 4, 6, 3, 7, 8, 6? We can plot these points now by inserting a chart like this, a scatter plot. And you can see they're not particularly linear. We have this 7, 6. Maybe we should move that point to something like 4, 6. That'll move that point over. Looks a little more linear now. Let's see if we can find that least squares line of best fit. To calculate those x squareds, I click on the x and square it, and the x times y's, we write equals x and then times the y. We need to paste these down. I'm going to grab the corner here and pull them down. And we need the sum of the x's. So I'm going to click on the auto sum button here and click enter. That's the sum of the x's. We'll have the sum of the y's, the sum of the x squareds, and the sum of the xy's. Now, we need to calculate m and b. According to our formula, the formula said that m is the sum of the x's times the sum of the y's, minus n, which in this case is 6, times the sum of the x times y's, divided by the sum of the x's squared minus n, which was 6, times the sum of the x squareds. This will be the slope of the least squares line of best fit. Now for the intercept, the y-intercept. That's going to be the sum of the x's times the sum of the xy's minus the sum of the y's times the sum of the x squareds, divided by the same denominator as before. That was the sum of the x's squared minus n, which was 6, times the sum of the x squareds. So we have a y-intercept of 1.27-ish. Now, there is another way to do this. We did it the old-fashioned way, using the formulas for the critical point for the least squares line of best fit using methods from Calculus 3. Of course, if we want to just insert a chart in Excel, well, I don't want bubbles. There, like that. Where did this point come from? Oh, yeah, we don't want to insert all of those. We just want the first few, right? So the others are, that last point is wrong. We need to insert a chart, XY chart, like this. The way that you can calculate these is to add a trend line, and you want to make sure to display the equation of the trend line in the chart. I'll move that up here so we can actually see that Excel gives us the same slope and intercept that we found independently. It's using exactly the same method to find that least squares line of best fit, and it's drawing it right here. There is yet another way to find the least squares line of best fit. The way to do this is to type the word slope. And the way Excel works is it wants you to put the known y's first, comma, the known x's. I don't know why it wants you to put the y's first and then the x's, but it does. And there it is. And intercept. And again, known y's, comma, the known x's. And that will give you the intercept. The nice thing about either knowing the formula or knowing the command is that you get a lot of extra digits that maybe Excel
just displays whatever number of digits it displays on the chart and doesn't give you a lot of freedom in choosing the number of digits. In any case, I thought you would appreciate seeing how to do this on a spreadsheet program.
I would now like to talk about Lagrange multipliers. This is a form of constrained optimization. Constrained optimization problems begin by trying to find the maximum or the minimum of some objective function. But it's subject to some constraint or constraints. We'll describe these constraints here by g of x comma y equal to 0. If we think of z equals f of x comma y as a surface, the equation g of x comma y ends up being a curve in the domain, and that may give us some curve up on the surface. The maximum value and the minimum values on some closed and bounded curve, the curve being closed and bounded, will satisfy the properties of the extreme value theorem, and hence if this function is continuous, we will achieve both an absolute max and an absolute minimum on that curve. So how do we solve these constrained optimization problems? We're trying to find the maximum or the minimum of some objective function subject to one or more constraints. Before going on and explaining how it is that we're going to solve these, let me describe for you an example of where I have actually used one of these problems in my own life. When I was getting ready to go to my master's degree program, I knew that I wasn't going to be earning a lot of money. The college was going to give me, in exchange for teaching a class, $450 per month. Now, I did get my master's degree at Idaho State University in Pocatello, Idaho. So you have to consider also this was 1989. But even at that time, living on $450 a month was difficult. I was able to find an apartment, a basement apartment in Pocatello for $120 a month. Score. All I needed to figure out was how to eat. The electricity ended up being quite affordable, even during the worst winters, well below zero for weeks. I only had to pay maybe $7 a month for my heating bill. It was amazing. Food really was the limiting constraint. I could walk to the university from my basement dwelling, and so transportation was not an issue. The only difficulty walking was whenever there was a blizzard blowing through, with snow going sideways, I'd have to walk through the snow and the strong heavy winds and the drifts of snow. There was usually about a foot of ice on the city streets, so it was quite a hazard. Nonetheless, I determined that I was going to find the optimal diet. I was going to find the diet that had minimum cost. I was going to minimize the cost function for my diet, subject to the constraint that I get all of my nutrients. I get enough calories, I get enough vitamin A, vitamin B, vitamin C, all of my proteins. I was going to have the optimal diet. And so I went to the store and I priced various acceptable foods. And I bought a nutrition almanac. And the nutrition almanac had the different amounts of the various nutrients for each of those foods. I had a handheld calculator that was programmable. I programmed that calculator to solve this constrained optimization problem for me. And it ran for 20 minutes. I was afraid I would run out of batteries. It was running so long. And it finally gave me the answer of the optimal diet, the cheapest diet that would give me my various nutrients. And it told me I needed to eat beans and brown rice. Yes, maybe a little spinach, maybe a little vitamin supplement added in there, but it told me beans and brown rice. I guess any mother could have told me that. Nonetheless, I'm going to show you how to solve constrained optimization problems, and these have applications all over the place. It's a method called Lagrange Multipliers. The theorem goes like this. Suppose f is differentiable on an open set. We'll say in R2, we'll assume f has variables x and y. We could extend this to x, y, and z, in which case we'd have to use R3 or so on, but I think you'll understand. Which contains a smooth curve given by g of x comma y equals 0. There's your constraint. The open set has to contain the smooth curve. If f has an extremum on g at x naught, so you have a maximum or a minimum of f constrained to be on the curve at x naught, then x naught is a critical point of a very special function, the function h of x comma y comma lambda. There's your Lagrange multiplier. F of x comma y minus lambda g of x comma y. So you're going to construct this function big H by taking the objective function f and subtracting a Lagrange multiplier times the constraint function. The critical points of this are where you need to hunt for the extrema of the function f on the curve g. Let's prove this Lagrange multiplier theorem. Suppose r of t equals x of t, y of t is a parameterization of the curve g of x, y equals 0. So if I plug these functions in, I will get 0 for all t. We'll consider f evaluated on that curve. In order to find the extrema, we take the derivative with respect to t and set it equal to 0. It is differentiable after all. And then solve for t. But this is a classic chain rule problem. That's going to be df dx dx dt plus df dy dy dt. And this looks an awful lot like a dot product. It's the dot product of df dx, df dy, and the tangent vector dx dt, dy dt. equal to 0, which means these vectors are orthogonal. We have 0 equals the gradient of f dot dr dt, the velocity vector to the curve, which is tangent to the curve. We deduce then that the gradient of f is orthogonal to dr dt. Now, also, the gradient of g must also be orthogonal to the level curves, and hence grad g is also orthogonal to dr dt. We deduce then that grad f is parallel to grad g. What does that mean? Two vectors are parallel if there's a scalar lambda, so that grad f is lambda times grad g, which implies that the 0 vector is grad f minus lambda grad g. Now let's look at the components here. The 0 vector will be df dx, comma, df dy minus lambda dg dx, comma, dg dy. When you think about it, df dx minus lambda dg dx and df dy minus lambda dg dy are exactly dh dx, dh dy, and both of those have to be equal to 0 if h, which was a function of x, y, and lambda, truly is f of x comma y minus lambda g of x comma y. Then the critical points of h satisfy 0 equals dh dx, which is df dx minus lambda dg dx. 0 equals dh dy, which is df dy minus lambda dg dy. And 0 equals dh d lambda. The derivative with respect to lambda is just minus g of x comma y, which is the same if we multiply through by a negative as g equals 0. We've built this in to our proof by assuming that our curve r of t is a parameterization of exactly this curve. So obtaining these two equations as necessary conditions for the extrema, the proof really is over at this point. As an example, suppose we want to find the max and the min of z equals x squared plus y squared. This, by the way, is an elliptic paraboloid subject to the constraint, let's say x squared plus xy plus y squared minus, I don't know, 7 equals 0. What kind of curve is this? This is a conic section, is it not? You can tell what kind by looking at b squared minus 4ac. Because it's negative, we get an ellipse. So we have some rotated ellipse in the plane here. This corresponds then to some curve on the elliptic paraboloid. Some kind of a curve looks like a roller coaster ride. There must be both an absolute max and an absolute min on that curve. This is a closed and bounded set, and this is a continuous function defined on this closed and bounded set. The extreme value theorem guarantees the existence of both an absolute maximum and an absolute minimum on that curve. We just need to find it. So to do this, we'll set up this function h, which is f minus lambda g. It's going to be x squared plus y squared minus lambda times the quantity x squared plus xy plus y squared minus 7. And then all we have to do is find the critical points of the function h. Once we know the critical points, we'll plug those into the objective function and determine which ones give us the largest values and which ones give us the smallest values. So first, hx. We'll have 2x minus lambda times 2x plus y. hy is 2y minus lambda times x plus 2y. H lambda equals 0 always gives you the constraint back. So to these I'm just going to add x squared plus xy plus y squared minus 7 equals 0. Here we have three equations in the three unknowns, x, y, and lambda. Now technically we don't really care what lambda is. We can eliminate that and then try to solve for x and y. To eliminate lambda from the first two equations, we can solve for lambda. On the first equation, we'll move this over. We'll have 2x divided by 2x plus y. When we solve for lambda in the second equation, we'll have 2y divided by x plus 2y. We'll set those equal to each other and then try to simplify as best we can. Let's cross multiply. We'll have x squared plus 2xy equals 2xy plus y squared. We can cancel the 2xy from each side, and we'll have x squared equals y squared. This gives us y is plus or minus x. We'll have to plug each of these lines into the constraint equation and solve those separately. First, we'll assume y equals x. We'll have x squared plus x squared plus x squared, and we'll move the 7 to the other side. 3x squared. X is going to be plus or minus the square root of 7/3. Y will be the same thing. We'll get these 2 points. Root 7/3, root 7/3, and negative root 7/3, negative root 7/3. And those will both be critical points. What about y equals minus x? In this case, we'll have x squared minus x squared plus x squared equals 7. That gives us x equals plus or minus the square root of 7. That gives us 2 points. Root 7 minus root 7 and minus root 7 root 7. We have 4 critical points. We need to evaluate these into the objective function to determine where we get the absolute max and where we get the absolute min. The function f, you'll recall, was x squared plus y squared. So when we evaluate f at root 7, negative root 7, we will get 7 plus 7, which is 14, but that will be the same value as negative root 7, root 7. Also, if we evaluate our function at root 7/3, root 7/3, we will get 7/3 plus 7/3, which is 14/3. But that gives us the same value at the other critical point, negative root 7/3, negative root 7/3. We have then an absolute max of 14 at these two critical points, root 7, negative root 7, and negative root 7, positive root 7. We have an absolute min of 14 thirds at root 7 thirds, and negative root 7 thirds, negative root 7 thirds. In our next example, I want to find the absolute minimum, 2x squared plus y squared plus 3z squared, which is kind of a four-dimensional analog to the elliptic paraboloid. If this is equal to w, you have x, y, z, and w as your variables. X squared, y squared, z squared, these are all squared. You end up with a paraboloid, and it will open up in 4 dimensions. But here we're subject to the constraint. Obviously, there is no maximum to such a thing. There should be a unique minimum, but we're not going to take the minimum value altogether. That would be 0 at x equals 0, y equals 0, z equals 0. We want the minimum obtained on the following constraint. 2x minus 3y plus 4z equals 49. This is a plane. In R3, it would be a hyperplane in R4 with w unconstrained. So, we're taking this plane and slicing it through this elliptic paraboloid in 4 dimensions, and we obtain a closed and bounded region. According to the extreme value theorem, this must have both an absolute max and an absolute min when taken together. So, the first step is to form the function h, which is the function f, the objective function, minus the Lagrange multiplier lambda. This is the lowercase Greek letter lambda. The uppercase Greek letter looks like this. It's spelled L-A-M-B-D-A, lambda. We'll put the constraint here, 2x minus 3y plus 4z minus 49. We don't really need to solve for 0 because we're always taking derivatives and setting them equal to 0. The derivative of a constant will be 0. So we don't need this term here at all. Critical points will satisfy all derivatives equal to 0. So hx equal to 0 will be 4x minus 2 lambda. Hy equal to 0 will be 2y minus a negative 3 lambda. 0 equals hz will give us 6z minus 4 lambda. And then to these 3 equations in 4 unknowns, we add the constraint. 2x minus 3y plus 4z equals 49. 4 equations in 4 unknowns. I have found that students have the most difficulty solving these systems of equations. So do as many problems as you can so you can work out the kinks in your algebraic skills. Yep, as per usual, algebra is the biggest obstacle. On the first equation, if we solve for lambda, we'll get lambda equals 2x. And on the second equation, if we solve for lambda, we'll get lambda is negative 2/3 y. And on the fourth equation, we'll get lambda is 3/2 z. If we take these first two equations together, we have 2x equals negative 2 thirds y. We can cancel the 2 off and multiply the 3 over and the negative and get y is negative 3x. If we take the first and third equation together, we'll have 2x equals 3 halves z. Solving for z, we'll have 4 thirds x. Now, we'll take these two equations and replace y and z with quantities involving x. We'll have 2x minus 3y. That's going to be minus a negative. 3 times 3 is 9x. Plus 4z. That's going to be plus 16 thirds times x. Still equal to 49. 9 and 2 makes 11. 11 is 33 thirds. Plus 16 makes 49 thirds. We can cancel the 49 off and move the 3 over. We get x equals 3. Once we know x is equal to 3, we can solve for y and get minus 9. And then solve for z and get 4. We have a unique critical point. This must give us the absolute min. You'll recall that the objective function was 2x squared plus y squared plus 3z squared. Evaluating f at the critical point we have 9 times 2 is 18 plus 81 plus 16 times 3, which is 48. We have 99 plus 48, that's 147. So we have an absolute min of 147 that occurs at the critical point 3, negative 9, 4. In our next example, I'm going to show you a new feature. I want to find the max and the min of the objective function 20 plus 2x plus 2y z squared, subject to two constraints. These constraints are x squared plus y squared plus z squared equals 11. This is a sphere of radius square root 11. That is a closed and bounded set already, but we're going to add another constraint. The other constraint is x plus y plus z equals 3. So we're taking the sphere and slicing it with this plane. That should give us a circle, which is still a closed and bounded set. So by the extreme value theorem, this continuous function on this closed and bounded set will attain both an absolute maximum and an absolute minimum. All we have to do is find it. We'll use Lagrange multipliers, but there has to be two multipliers this time because there are two constraints. So the function h is going to be the objective function 20 plus 2x plus 2y plus z squared minus, I'll use alpha, x squared plus y squared plus z squared, and minus 11, which doesn't really have to happen, minus beta times x plus y plus z minus 3. There are 5 variables this time, x, y, z, and alpha and beta. We find the critical points of h by calculating the partial derivatives, setting them equal to 0, and solving for x, y, and z, eliminating alpha and beta. We'll have 2 minus 2x alpha minus beta. 2 minus 2y alpha minus beta. and then 2z minus 2z alpha minus beta. That's 3 equations in 5 unknowns. To these we slop on the constraints. Yielding 5 equations in 5 unknowns. Now to solve these equations. If you set the first 2 equations equal to each other, you can cancel the 2's, cancel the betas, cancel the negatives, and then cancel these 2's. You'll end up with x alpha equals y alpha. Before you start canceling alpha, you want to put everything to one side and factor the alpha out. Then we get the zero product theorem coming into play. We have the product of 2 things equal to 0. Either x equals y or alpha equals 0. You can see if you just lop the alpha off, you'll lose this whole solution, alpha equals 0. We have to pursue both of these possibilities. So first, let's assume alpha is 0. If alpha is 0, we deduce then that beta is 2. If alpha is 0 and beta is 2, then z is 1. If z is 1, we can plug that into the constraint equations and reduce those to x squared plus y squared equals 10. 1 squared is 1, subtract it to the other side, and also x plus y equals 2. We have a circle and a line intersecting each other. We expect to get 2 points of intersection. Solving for y is 2 minus x, we'll substitute that into the first equation. That gives us x squared plus 2 minus x quantity squared equals 10. We'll have x squared plus another x squared is 2x squared minus 4x plus 4 minus 10 is minus 6 equals 0. We can divide the 2 off and then factor. This gives us x minus 3, x plus 1 equals 0. So that x is either 3 or minus 1. We can find the corresponding y from that. If x is 3, then y is minus 1, and z is still 1. If x is minus 1, then y is 3, and z is still 1. This gives us 2 critical points. We now need to pursue the other option, x equals y. If we assume x equals y, we can eliminate y from both of the constraints. We'll have x squared plus x squared plus z squared equals 11, and then x plus x is 2x, plus z equals 3. Solving for z is 3 minus 2x. We can substitute in and get 2x squared plus 3 minus 2x quantity squared equals 11. We'll have 2x squared plus 4x squared is 6x squared minus 12x plus 9 minus 11 is minus 2. We can divide a 2 off and get 3x squared minus 6x minus 1 equals 0. What are the solutions of this quadratic equation? We find the solutions by the quadratic formula. X equals minus b plus or minus square root b squared minus 4 times 3 times negative 1 all over 2a. 3 times 4 is 12, plus 36 is 48. 48 is 16 times 3, so we end up with 6 plus or minus 4 root 3 over 6. That gives us 1 plus or minus 2/3 times the square root of 3, and that must also be y. The z-coordinate is determined by z equals 3 minus 2x. 2 times 1 plus or minus 2/3 root 3. We'll have 3 minus 2 is 1. When we subtract a plus or minus, we get a minus or plus. We'll have 4 over 3 root 3 for the z-coordinates. We end up with 2 critical points. The additional critical points are 1 plus or minus 2/3 root 3, 1 plus or minus 2/3 root 3, and these pluses and minuses are not independent. We had x equals y, so if you have a plus in the first coordinate, you must have a plus in the second coordinate, etc. The last coordinate is 1 minus or plus 4/3 root 3, and again, if you have a plus on the first two coordinates, you get a minus on the third coordinate, etc. So this is only 2 additional critical points. We have 4 critical points altogether to test. We need to evaluate the objective function at each of these 4 critical points to determine the size, which is the max and which is the min. Remember that the objective function was 20 plus 2x plus 2y plus z squared. If we evaluate f at 3 minus 1, 1, we'll have 20 plus 6 minus 2 plus 1. And that gives us 25. We'll get the same thing at negative 1, 3, 1. Switching 3 and negative 1 between the x and y will not change the outcome in terms of the computation. So both of these critical points give us a value of 25. What about the additional critical points? We're going to try to evaluate these both at the same time. We take 20. Since x and y are equal, we'll have 4 times 1 plus or minus 2/3 root 3. And we square the last term. When you square this, you'll get 1 minus or plus twice the product plus the last term squared. Oops. When you square the denominator, you get 9. When you cancel, you end up with 3 in the denominator. So how does this all work out? When we distribute the 4 here and combine this 1 with the 20, we will get 25. Then we'll get plus or minus 8/3 root 3. But we also get a minus or plus 8/3 root 3. So these terms actually cancel. We finally have plus 16/3, which is 5 1/3. We have then 30 1/3 is the absolute max, and 25 is the absolute min. The first critical points that we found are the locations of the absolute minimum, and the second pair of critical points is the location of the absolute maximum. On the diet example I mentioned earlier, I used a special method that works for linear constraints and linear objective functions called the Simplex Method. I learned this method in a course called Operations Research that I took as an undergraduate. Operations research is a subject that applies mathematical techniques to solving business problems. So, you never know when you might have a chance to use these different methods. I'm certain that in some engineering problem in your future, you'll find an application to Lagrange multipliers.